Today we're going to talk more about rotation estimation. It won't even be the final form, but this is the key ingredient for the factoring algorithm. And it's also a key ingredient in wrapping up Grover's algorithm. So where were we last time? We were talking about the rotation estimation problem when you have a 1-qubit operator, and we achieved this result that Caldwell called relative error. So the setup there is that you have some mystery rotation operation that rotates 1 qubit and by some unknown angle theta. And we're trying to estimate this theta, and we had like a somewhat simplifying assumption that it's between 0 and 30 degrees. And what we saw is that with a number of calls to mystery rotation, a number of measurements as well, that's proportional to 1 over theta, you could estimate theta pretty well. You could estimate it to within factor 2. Okay, so theta could be like 10 to the minus 10, and then you'd figure out that it's somewhere between 10 to the minus 10 times 0.5 and 2 times 10 to the minus 10. Okay, so a couple things we want to get to. We want to get to an even better factor. We want to get to like within 1%. This is something I promised you like 2 lectures ago. And then in this lecture, we're going to try to get even more precision than that. So let's see how we're going to do that. So how do we get this? You might remember we used the strategy of taking the rotation, rotating a bit, and keeping rotating until we got to this medium-like angle, which we could kind of notice. So we had this algorithm factor 2 estimate, and it tried powers of 2, k, like 2, 4, 8, 16, and so forth. And it considered mystery rotation that you did like k times in a row, and that subroutine has a rotation angle of k times theta, and it kept testing it out until it sort of found that k theta was between, somewhere in the neighborhood of 45 degrees, so between 22.5 degrees and 67.5 degrees. And then it was like, okay, great, 45 degrees is like a pretty good guess for k times theta. It's within factor 2 of k times theta. Okay, and then you just divide this equation by k, and you get that this estimate, 45 degrees divided by k, is within factor 2 of theta, which was your goal. Great. So now, I said last time, one thing I promised you is that we get this down to like not just factor 2, but like get something within 1% of theta. So let's start with that. So let's estimate theta to within 1%. And I want to stress that here, by what I mean by this is within 1% of theta itself. So that's why it's called relative error. Your error is relative to the quantity you're trying to estimate. So if it's a really tiny quantity, you need a really tiny error. And if it's a really big quantity, then you don't need such a good error. So what we're actually going to do is estimate k times theta to within 1%, this sort of medium number. And that's fine for relative error, because if you estimate k times theta to within 1%, then you just divide that estimate by k, and you're estimating theta to within 1% as well. Because always, as I said, this is within 1% of the thing you're trying to estimate. And what I claim is that now that k times theta is like a nice big number, like around 45 degrees, it's not so hard to estimate this, quite precisely with a constant number of calls to this mystery rotator. So I claim that it's sufficient to estimate k times theta to within, I'm going to write like a pretty specific looking number, but don't stress too much about this pretty specific number, plus or minus 0.004, okay, radians. And this is what I call an additive error, like an absolute error. That's in the title here. It's not relative to the value of the thing you're trying to estimate. It's just literally plus or minus some number, 0.004. Okay, so why is this enough? Well, I just claim that this additive error is smaller than 1% of the thing that you're trying to estimate, which is just a little numerics that I will verify for you. It's because, as I claim, 0.004 is less than or equal to 1% of k times theta. Well, wait, why is that true? Well, because k times theta, we've gotten it up so that it's at least 22.5 degrees. Okay, and that's about 0.4 radians. Okay, and so 1% of k theta is at least 1% of 0.4, which is 0.004. Okay, so by virtue of this, all that remains for like our old kind of problem of estimating theta to within 1% of itself is this task, estimating this like nice big medium number k times theta to within plus or minus 0.004, or just 0.004 is some small absolute constant. Okay, well, that's why I wrote this on the board. This is what we're going to work on pretty soon. And this is very similar, by the way, to the is medium algorithm from last time. So let me read it out to you. So we're going to be given access to, once again, a 1-qubit mystery rotation operator, but I called it mystery rotation prime because once we prove this theorem, we're going to apply it. I can get this marker out. We're going to apply this theorem with this mystery rot prime being this mystery rot to the power of k. And it's assumed to be acting by some rotation theta prime. So theta prime, when we apply this theorem, will be k times theta from over here. That's between 0 and 90 degrees. And so this theorem that we'll prove relatively soon will estimate this angle of rotation theta prime to within plus or minus 0.004 as desired. And this theorem will need to make a number of calls to the mystery rotator, which is like an absolute constant, like just a totally fixed constant. It'll be around 100,000, but that's a constant. That's completely fixed, depends only on this error. And then we're in good shape because this final estimator will make constantly many calls to mystery rot prime. Mystery rot prime over here is mystery rotation to the power of k. That means doing this mystery rotation k times. So overall, we'll call this constantly many times. And so we'll get constantly many times k calls to the original thing that we really wanted to work on over here. Okay. And this order 1 over k, or order k, because k theta is approximately 45 degrees, this is literally a constant, that means that k is proportional to 1 over theta. Okay, so finally, this is the order 1 over theta when he calls the mystery rotation algorithm. Okay, so this is like a little dipsy doodle to like convert this task of estimating theta to within 1% to estimating this big angle k theta to this fixed constant additive. Okay, any questions about this? Okay, so we're going to get to this in about 10 minutes, but there's one more thing that, like, annoyingly, we have to take care of, and it's the following. This algorithm and this algorithm that we're going to talk about are all in this like kind of simplified abstract setting where like you get access to quantum subroutine that just operates on 1 qubit and rotates 1 qubit. But if you think about the application to Grover's SAT algorithm and you really want to like put all the pieces together and get, your square root 2 to the n times SAT algorithm, you'd be like, well, we actually weren't in such a simple scenario there in Grover's algorithm. Remember, in Grover's algorithm, you had this giant 2 to the n dimensional space, and you had this vector ket uniform, which you can make yourself, and you knew how to rotate it in some mystery direction, and you were trying to rotate it like 90 degrees. So it wasn't just like you had like 1 qubit, and it was like ket 0 and ket 1, and you knew exactly what was going on. It was a bit more subtle than that. So let me illustrate or just write down the difference. The punchline is going to be that, like, even though it's like a somewhat more complicated setting, we can still port all this rotation estimation code to also work in that setting. So everything's fine, but, well, we have to actually do it. So this simple setting that we've been talking about for rotation estimation is what you might call like a known 2D plane setup. And what it means is mystery rotation, your subroutine that you're working on, acts on a 2D plane that like you exactly know. In fact, it's just, the 1-qubit plane of ket 0 and ket 1. Okay, so there's absolutely no mystery about where it is. Like, you know how to create ket 0 if you want. You know how to create ket 1 if you want. You could rotate the plane by 30 degrees yourself if you wanted. You know everything about like where the action is happening. Now, in the Grover setting, it's not quite as simple. I'm going to call it the semi-known 2D plane case. Semi because you know one of the vectors in the 2D plane, or like one of the vectors in the 2D plane is easy for you to create and set up. So like we, or the algorithm, know one vector, namely this ket uniform in the 2D plane of rotation that we care about or we're analyzing. But we don't know the other one. So the other, important vector in this 2D plane in the Grover setting is this one called ket goal, or in the simple case where there's only one satisfying string, it was like ket x star. But we don't know it. Our whole goal is in fact to find it. So it's like we know how to make uniform, and then like we know we have this rotation operation that starts rotating it in some direction we don't really know about, and we're trying to rotate it like about 90 degrees in this direction we don't really know about. So we know like some stuff about the plane, but not everything. And so you kind of have to think back a little bit to like how, our mystery, our rotation estimation algorithm worked. So let's just think about, how it worked. Well, how did it work to estimate theta, to within factor 2? Well, you start out by making a new qubit in the state ket 0, and then you do the mystery rotation and get it at angle theta, and then you'd measure. And you do this like 100 times in this like sort of is medium subroutine to try to find out, hey, is theta kind of, between 30 and 60 degrees or something? And if it was, you'd be like, great, now I know it's within factor 2. But probably it wasn't. Probably all your measurement outcomes came back ket 0. And so you're like, okay, now I'll try double that angle. So you'd, again, prepare ket 0. And now you do mystery rotation twice to make the angle twice as big. And then you'd measure, see if you got 1. You do that 100 times, and probably they'd be all zeros. So you'd be like, all right, I'm going to try 4 times mystery rotation, and 8 times, and 16 times. Always measuring, this 1 qubit and seeing if you got 0 or 1. And finally, you wait until like the 100 times you do it, like you got like a decent number of 1s. You're like, now I know that my current multiple of theta is, around 45 degrees. So can we do this in the Grover setting? Well, some things work fine. So the analog of, ket 0, the sort of the vector you start at, is ket uniform. And that's fine. We know how to make ket uniform. It's easy. You just make all zeros and do the Hadamard transform. So we kind of know how to get started with ket uniform. And, we have this Grover rotation operator R that is our mystery rotation. So we know how to rotate. But what about the measuring part? So how do we get at that? You see here, what we used is that, in this is medium, we used the following, that if the state vector, I might run out of space here, is at angle alpha from the sort of the starting vector, ket 0, then we could just extract this bit, and we'd see, sorry for this terrible board usage, extract, and we'd see, 1 with probability sine alpha squared. Okay, and we, made this angle alpha, tried it like larger and larger until such time that like alpha was in the neighborhood of 45 degrees. And so therefore sine alpha squared is in the neighborhood of a half. And so we saw vaguely around 50-50 many ones. So we need like to be able to get a similar situation here. Okay, so what I'm saying is like in the Grover setup, we need to, once we, get our state vector at some angle alpha, some multiple of or power of 2 times theta away from ket uniform, we need to do some kind of measurement that gives us some kind of signal with probability sine alpha squared. So how do we do this? In the Grover setting, well, we just need to like rotate our world so that this starting vector, ket uniform, becomes like the all zeros vector. And then we can just do the usual measurement there, and things will be in good shape. So what do I mean by that? So the changes that we need to do from the 1 qubit algorithm, we need to replace, making a new qubit and getting ket 0. We need to replace this with just, preparing ket uniform. Okay, which we do by making, n new qubits and doing the Hadamard transform. And we need to replace, extracting the 1 qubit and checking for outcome 1, which let me call this not 0. We replace it with this subroutine. So 1, like imagine in the Grover setting, you prepare this ket uniform, you do some rotation. So now you're at angle alpha, and you're like, okay, I want to try to measure this. What you do is Hadamard all. And the point of this is it like rotates space so that ket uniform goes back to all zeros. And remember, Hadamard all is its own undo. So like Hadamard all, it takes all zeros to uniform, but also takes uniform back to all zeros. And then you do your measurements. You do extract all. And then basically you check if the outcome is not all zeros. Okay, which is like the analog of checking that it's like not 0. And why does this work? Why does this do what we want? Well, suppose that in the course of this Grover setting, you got the angle, the state vector to be some alpha. Before line 1. When you sort of try to do your new kind of measurement. So then after line 1, the state vector is at angle alpha from all zeros. Okay, because this is a unitary transformation, so it doesn't change angle. So if state vector used to be at angle alpha from uniform, and we do this, now the state vector is at angle alpha from wherever this goes to, which is all zeros. Okay, and what does that mean? So it's of the form. So what does a state look like if its angle is alpha from all zeros? Well, it's got some amplitude on all zeros, and that has to be cos alpha. Because we know the inner product of what does it mean to be at angle alpha? It means your inner product with this vector, your dot product with this vector is cosine alpha. So it means to be at angle alpha. So the dot product of the state vector with all zeros should be cosine alpha, plus some other amplitudes on dot 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 1, plus some other stuff. But the point is you have like this amplitude on all zeros. So then in line 2, when you extract all, the probability you get the outcome all zeros is the square of the amplitude on all zeros, which is cos alpha squared. And therefore, the chance that you get not all zeros is sine alpha squared. Okay, because this should just be 1 minus this, and we know that sine alpha squared and cos alpha squared add up to 1. Okay, so this was like one final detail I needed to check for you, that you can basically accomplish the 1 qubit rotation estimation algorithms we've been talking about in the more complicated Grover setting, because really you just need to, in the 1 qubit rotation estimation, you just need to sort of like measure against your starting vector. And in the Grover setting, we know how to measure against the starting vector. You just move the starting vector back to all zeros and do a regular measurement.